In this example, we will find the derivative of arcsecant of x. Arcsecant of x is an interesting function, but it's not something that we frequently use. So let's quickly review how the graph of the function looks like, what is domain and range. When I want to graph secant of x, because it's defined as 1 over cosine of x, it means that whenever cosine of x is equal 1, secant would be 1. And whenever cosine is equal to minus 1, 1 divided by minus 1 is also minus 1. So those are the common points between the cosine and the secant. Now, when cosine approaches 0, 1 over cosine goes to either plus infinity or minus infinity. Therefore, wherever cosine is equal to 0, secant has the vertical asymptote. The inverse functions only exist if we are able to tell back exactly which input was used to create a specific output. So, in order for us to define arcsecant, the first step is to restrict the domain of the secant. We need to find the smallest interval possible where all the outputs of the secant are present, but we would be able to identify exactly which input was used to produce each specific output. And as you can see, the example of the interval would be from 0 to pi, not including pi over 2, because secant is not defined at pi over 2. Now we have a restricted domain for the secant, and we know the range. The secant of theta produces outputs either greater or equal 1 or less or equal than minus 1. Now that we have the two branches for the secant that we're going to use, we can create the reflection of those graphs with respect to line y equals x. We'll sort of switch points. We'll take a point with coordinates xy and switch x and y places, creating a new point with coordinate yx. And this new graph will be the graph of our inverse. If we take a point on a graph of a secant, 0, 1, then the inverse trigonometric function would have a point on its graph with coordinates 1, 0. Whatever was our vertical asymptote, it happened to be x equals pi over 2. For the inverse function, it would be horizontal asymptote, y equals pi over 2. And the point with coordinates pi minus 1 for the original function would be flipped into the point with coordinates minus 1 pi for the inverse. And knowing all that, now we can sketch arcsecant of x. Arcsecant of x has the domain where x is less or equal than minus 1 or x greater or equal than 1. And the range is from 0 to pi, but not including pi over 2. It's fun to see the graph arcsecant before looking for the formula for the derivative, because now on the graph we can imagine drawing tangent lines anywhere on the curve, and you notice how the slope of those tangent lines are always positive, no matter which value of x we'll select from the domain, wherever the tangent lines can be drawn. Okay, now actual derivation. As of right now, we don't know how to calculate derivative of arcsecant. So our goal is to manipulate equation y equals arcsecant in such a way that arcsecant is no longer present in the equation. Let's take it out by taking a secant of both sides of the equation. We'll get secant of y equals secant of arcsecant of x. Secant of arcsecant of x is just x, because f of f inverse of x is equal to x. That's how inverse functions are defined. Therefore, now we have new much simpler equation, secant of y equals x. And we know how to differentiate secant, and we know how to differentiate x. We just need to be very careful, use implicit differentiation and the chain rule. So, derivative of secant of y is equal to secant of y times tangent of y times derivative of y with respect of x. This is equal to derivative of x with respect of x, which is just 1. We're looking for dy dx, so dy dx will stay on the left side of the equation and we'll divide by secant of y and divide by tangent of y to move the secant and tangent to the right side of the equation. Now we have expression dy dx equals to 1 divided by secant of y times tangent of y. Secant of y is exactly equal to x, so that's an easy substitution back. What is tangent of y in terms of x? Well, we have seen equation sine squared of an angle plus cosine squared of an angle equal 1. If we'll take this equation and divide by cosine squared, we'll get a new equation. Tangent squared plus 1 equals secant squared. We can write tangent squared of y as secant squared of y minus 1. But in our expression for the derivative, we don't have tangent squared, we have just tangent. So let's take square root of both sides of the equation. Square root of tangent squared of y equals to square root of secant squared of y minus 1. Square root of tangent squared of y is an absolute value of tangent of y, which is equal to something we cannot simplify any further, that's square root of secant squared of y minus 1. The tangent of y can be either plus square root of secant squared of y minus 1 or minus square root of secant squared of y minus 1. Which is it? Is it plus or minus? If x is strictly less than minus 1, then we know that arcsecant of x would be producing values of y between pi over 2 and pi. Then what's tangent of y if y is between pi over 2 and pi? Well, whatever it is, it's going to be a negative number. Therefore, if x is less than minus 1, we have to replace the tangent of y with the negative square root of secant squared of y minus 1. And of course, the secant of y is exactly x, so the tangent of y would be replaced by minus square root of x squared minus 1. What happens if x is greater than 1? Well, by looking at the graph of arcsecant, we know that if x is greater than 1, then the outputs for arcsecant are between 0 and pi over 2. So what happens with tangent of y if y is between 0 and pi over 2? Well, tangent is positive. Therefore, the tangent of y will be replaced with positive square root of x squared minus 1. It means that now we have two formulas for the derivative of arcsecant. The derivative of arcsecant of x is equal to negative 1 divided by x multiplied by the square root of x squared minus 1 if x is strictly less than 1. But the different formula would be if x is greater than 1. The derivative of arcsecant would be positive 1 divided by x multiplied by the square root of x squared minus 1. We can combine this together if we write the derivative of arcsecant of x is equal to 1 divided by absolute value of x multiplied by the square root of x squared minus 1. Absolute value of x is going to be positive for positive value of x as well as the negative value of x. This will ensure that we have just one way of writing that actually captures both scenarios where x is greater than 1 and when x is less than minus 1. So then, whenever we'll see the derivative of arcsecant, we know that the formula is 1 divided by absolute value of x multiplied by square root of x squared minus 1, as long as absolute value of x is strictly greater than 1. If absolute value of x happens to be equal to 1, it means x is either 1 or minus 1. And if you look at the graph of the arcsecant again, you will notice how the slope of a tangent line becomes steeper and steeper and steeper, more and more and more vertical as x approaches either minus 1 from below or plus 1 from above. So the derivative at minus 1 and at 1 does not exist.